Welcome to Ask and Learn.
For this problem on the topic of equilibrium of rigid bodies, we are told that a vertical load is applied at the end of a rod as shown in the diagram. We are given the constant of the spring to be K, and we are given the angle theta when the spring is unstretched. We want to calculate or express rather the angle theta corresponding to the equilibrium position in terms of P, K, and L. We then want to determine the value of theta if we are given a value of P at equilibrium. So here we have a free body diagram of our rod. We can break up the reaction force C into its X and Y components. The load P acts vertically downwards, and the T is the force along the spring. Now we can see the triangle ABC is isosceles, and so we have AB equal to 2AD, which is 2L sine theta over 2, and CD is equal to L times the cosine of theta over 2. Now for the elongation of the spring, we'll do the following. So the elongation of the spring we'll call X, and X is equal to 2L sine theta over 2 minus 2L sine 30 degrees. Now we have an expression for the elongation of the spring, X, and we can write an expression for T. So we know the force acting on the spring by Hooke's law is Kx. So we can write this as, by substituting the expression for X from above, as 2KL into sine of theta over 2 minus sine of 30 degrees at equilibrium, which is a half. And now we can use this expression later on. So if we take anti-clockwise moments about point C, we know that the sum of these moments at equilibrium must equal to 0. So taking the sum of the moments, this is the force on the spring T times the distance L times the cosine of theta over 2 minus, in the opposite direction, the load P times L sine theta must equal to 0. So we can bring in our expression for the tension or the force on the spring T into this equation, and we can rewrite the second term as well. So we can write this as 2KL into sine theta over 2 minus a half into L cosine theta over 2 minus PL, and we can expand the L sine theta as a double angle expansion, so that's 2 sine theta over 2 cosine theta over 2. Remember, sine of 2 theta is 2 sine theta cosine theta, and all this is equal to 0. So this implies that either the cosine of theta over 2 is equal to 0, or 2 into KL minus P times the sine of theta over 2 minus KL is equal to 0. So the two solutions are that, trivially, theta must equal to 180 degrees, or the sine of theta over 2 must equal a half KL divided by KL minus the load P. And so we can write an expression for theta. So theta needs to be 2 times the arcsine of a half KL divided by KL minus P. So here we have an expression for the angle theta in terms of PK and L. And that's our answer for part A. Now for part B, we want to find this angle theta if we are given a value for P. So we are told that at equilibrium P is equal to 1 over 4 KL. And so if we go back to our expression for theta, or rather for sine theta, we have sine theta over 2 is equal to a half KL over 3 over 4 KL, which simplifies to 2/3. So this means that theta over 2 is equal to 41.8 degrees, which means that we can find theta simply in this condition to be 83.6 degrees.